In this question, we will look at the concept of half wave plate and quarter wave plate. So these wave plates basically change the polarization of the incoming light beam. So when we had a normal polarizer, let's say a normal polarizer, and this is, let's say, the transmission axis of the polarizer. So whatever polarization light might come in from here, the output polarization is always going to be along the transmission axis. So if we have some polarization like this, then only that part which is parallel to the transmission axis is going to get transmitted. So this is a normal polarizer. So this is the case for polarizers. Now in half wave plates and quarter wave plates, what happens is, let me draw first. So let's say we have a half wave plate. So this is half wave plate, and in half wave plate we have something known as the fast axis. So this is fast axis. In polarizer this was called transmission axis. In half wave plate it is called fast axis. And perpendicular to the fast axis is what we have known as the slow axis. So this is perpendicular 90 degrees. This axis is slow axis. And let us say we have some incoming input beam at some angle to the fast axis. So the output from this half wave plate would be such that it creates a phase difference of pi between the components along the fast and the slow axes. So let me write it down. So effect of half wave plate is to introduces phase shift of pi between the components of the wave along, let us call this fast as F and slow as S. So those directions. So it creates phase shift of pi between the components of the wave along the F cap and S cap directions. So phase shift of pi is being introduced between the components along the fast and the slow axes, and fast and slow axes are perpendicular to each other. So let us draw a 2D cross section of this half wave plate. So we have the fast axis and we have the slow axis, and we have the, so let me label it. So this is fast axis, this is slow axis, and this is 90 degrees, and the incoming light beam is along some polarization direction. Let us call it P cap. So let us write down the electric field. So incoming or incident electric field would be given as follows. And the polarization is along P cap direction. So this is basically like so. Now this wave, incoming wave, will have some component along the slow axis and some component along the fast axis. So let this angle be theta. Theta is the angle between the fast axis and the incoming polarization direction. So this can be written as like this. So this is the incoming electric field. Now after the half wave plate, what is the half wave plate? To introduce a phase shift of pi between the F and S components. So after half wave plate, we have the following. Plus phase shift of pi and e to the power I pi is nothing but -1. So this is the electric field after the half wave plate, when this was the incoming electric field. Now this can be rewritten in a slightly different manner. We know that cos of negative theta is cos theta itself, and sine of negative theta is minus sine theta. So using that trigonometric property, cosine minus theta is equal to cosine theta, sine minus theta equal to negative sine theta. Using these trigonometric identities, we have rewritten this as follows. So we see that we can write this effect by saying that the half wave plate has essentially mirrored the wave's polarization. So this is minus theta. Incoming wave had cosine theta and sine theta. Now we have cosine minus theta and sine minus theta. So if this propagation direction, if this direction is the z-axis, then essentially what the wave plate is doing, it is mirroring the wave's polarization vector through the plane formed by the fast axis f cap and z direction. So when we have a linearly polarized wave coming incoming electric field which is linearly polarized, then wave plate is essentially rotating the polarization vector through an angle 2 theta. This, if we draw the diagram, then the output electric field has a polarization along this direction, which is making angle minus theta. So this is, if the right side is positive theta, then the left side would be negative theta. So this is also theta, but in the other direction. So we see, so this is incoming and this is outgoing after the half wave plate. So essentially it has rotated the polarization by 2 theta. So this has gone to that, and this is rotation by 2 theta, or we can see it from here. This is rotation of 2 theta. So incoming to outgoing polarization is like rotation by 2 theta. This is for the case when the incoming electric field is linearly polarized. Similarly, we can see for the case of quarter wave plate. So this was the case of half wave plate. First we saw polarizer, then we saw half wave plate. Now let us look at quarter wave plate. So let us say that this is the quarter wave plate. Again, it will have a fast axis, and perpendicular to the fast axis we will have, draw it again, perpendicular to the fast axis we will have the slow axis. So this is fast axis, f cap direction, this is 90 degrees, and this is slow axis, s cap direction, and this is the propagation direction, z, and incoming electric field will have some polarization direction. So again, let us write for the incoming electric field. Incoming electric field, just like we did for half wave plate, it can be decomposed into components along the fast axis and along the slow axis. So we can write down the incoming electric field as some component along the fast axis plus some component along the slow axis, and then propagation term. So this is the incoming electric field. And after the quarter wave plate, we will have the following field. So we see that the effect of the quarter wave plate is to introduce a phase shift of pi by 2 between the components along the fast and the slow axes. So this is because I is nothing but e to the power I pi by 2. So we can write down effect of quarter wave plate is that it introduces phase shift of pi by 2 between the F and S components of the wave. So as the name suggests, half wave plate introduces phase shift of pi between the two components along the fast and slow axes, and quarter wave plate introduces phase shift of pi by 2 between the components along the fast and the slow axes. So this was about how half and quarter wave plates, and we had already seen the role of polarizer in the previous videos. So now let us look at the question that we need to solve. So let us write down the question. The question says, a half wave plate and a quarter wave plate are placed between two polarizers P1 and P2. All these are parallel to each other and perpendicular to the direction of propagation. Direction of propagation of light unpolarized light is incident on the polarizer P1 the optic axis, or same thing as the fast axis, so optic axis or fast axis, the optic axis of the half wave plate makes an angle of 30 degrees with respect to the transmission axis is also known as pass axis of P1. The optic axis or fast axis of the quarter wave plate is parallel to the pass axis or transmission axis of P1. The question has two parts, so it asks us to determine the state of polarization for the light beam after passing through the half wave plate and the quarter wave plate. The second part is what should the orientation of the pass axis of P2 be? This is with respect to P1 such that the intensity of the light beam emerging from P2 is maximum. Let us first draw the diagram of this question. So we have a polarizer P1, then we have a half wave plate followed by a quarter wave plate, and finally another polarizer P2. So this is P1, this is half wave plate, this is quarter wave plate, and this is P2, and this is the Z direction. So let us draw the other axis. This is X and this is Y. So basically X axis is going into the screen. So if we use a different notation, then we can say this is Y, this is Z. So X axis is going into the screen. We can use a symbol like this, a cross inside a circle. So let us say polarization of P1 is along the X axis. Then we are given that the transmission axis of P1 is, let's say, along the X axis. Then we are also given that for quarter wave plate the fast axis will be along the same direction as the transmission axis of P1. So let us assume, without loss of any generality, that both of them are along the X axis. And we are given that the fast axis of the half wave plate makes angle 30 degrees with the transmission axis of P1. So let us start solving the question. So we have unpolarized light incident on P1. This is unpolarized. And after the polarizer, we know that this would be polarized along the transmission axis of P1. So after the polarizer, the electric field would be, let us say, amplitude E0, and it will be, this is the transmission term, and the polarization would be along the transmission axis of P1, which we have taken in our case to be X axis. Now let us decompose this along the fast and slow axis of the half wave plate. But before that, let us draw a 2D diagram, the axis of the half wave plate. So let us say we have the x-axis, this is the y-axis, this also happens to be the transmission axis of x-axis, happens to be transmission axis of the polarizer. So this is the electric field after the polarizer. So this is E after P1, and the transmission axis, sorry, the fast axis of half wave plate makes angle 30 degrees. So somewhat like this. This doesn't look like 30 degrees. Let me try once again. So this is the fast axis of the half wave plate. So this we are drawing for half wave plate, this fast axis for half wave plate, and the slow axis is going to be perpendicular to this. So slow axis is going to be somewhat like this. This is the slow axis again for the half wave plate. This angle we are given is 30 degrees. So this angle automatically becomes 60 degrees. And this angle again, because fast and slow axes are perpendicular, this is 90 degrees. So this will become 30 degrees again. This angle is 60 degrees. So let us decompose this electric field after P1 along the fast and the slow axis. This is the slow axis, this is the fast axis. So this, let us say, is the positive direction for F, and this is the positive direction for S. So this is the decomposition along positive F and positive S, F cap and S cap. So this is the electric field after P1. Now after the half wave plate, a phase difference of pi would be introduced between the F cap and the S cap components. So after half wave plate, we will have the following: minus of cosine. So we just saw that only this phase of pi would be introduced between F cap and S cap components. So this would lead to this minus sign coming over here. We can have a look at it again. So if this was the incoming beam, cos theta F cap plus sin theta S cap, then after the half wave plate, we have cos theta F cap minus of sin theta S cap. So same thing we have written over here. So this is electric field after the half wave plate. So let us rearrange some terms. Cos 30 degrees is root 3 by 2. and cos 60 degrees is half. Now let us write f cap and s cap in terms of I cap and j cap, that is along x and y. So f cap would be cos 30 degrees I cap plus cos 60 degrees j cap. And s cap, this s cap right here is going to be cosine of 60 degrees I cap minus of this angle would be 30 degrees minus of cosine 30 degrees j cap. This is the positive s cap direction that we have taken. So let us put in the values for the cosine 30 degrees and 60 degrees. Cos 30 is root 3 by 2, cos 60 is half, sorry, this is half, so this gives us the following: 3 by 4 minus 1 by 4 is 2 by 4, which is half, plus root 3 by 2 j cap. So this is the electric field after passing through the half wave plate, and if we draw it on this axis, let me copy this diagram. So in this diagram, if we want to plot electric field after half wave plate, so let us erase a few things. Let me choose a different color. So initially electric field after P1, after the polarizer, was along x-axis. Now it is half along x-axis plus root 3 by 2 along y-axis times this amplitude. So if we draw that, we would get something like this. This is electric field after the half wave plate, and if you notice, this angle basically, this angle, this term basically corresponds to angle making 60 degrees with the x-axis. So this is essentially cos 60 degrees is half, So this is this term. So this angle right here, this angle, let me draw it in this color so that it's clear which angle I'm talking about. So this angle right here is 60 degrees, and this angle then would be 30 degrees. This angle 30 degrees. So this is in agreement of the statement that we had written, that a half wave plate rotates the polarization by 2 theta. If we see the previous statement that is there, this diagram. So effect of half wave plate is to introduce phase shift of pi between the F and S components, and that essentially makes theta go to minus theta. It's essentially kind of like reflecting the theta. So we see that it causes a 2 theta rotation of the incoming electric field. So this was our incoming electric field and this was our outgoing electric field, and we see that the polarization has been rotated by angle of 2 theta due to the half wave plate. So we see the same over here happening. So the half wave plate was making angle 30 degrees with the incoming polarization, which was after P1. So this has been rotated. So this has been rotated by 2 theta, that is by 60 degrees. So 30 degrees was our theta. Sorry about that. So 30 degrees is theta. So 60 degree, 2 theta is 60 degrees. So rotation from here to here, from E after P1 to E after half wave plate, this rotation, this diagram is getting too much cluttered, but nevertheless this angle, this rotation is 2 theta, which is 60 degrees. So everything is in agreement with what we have seen earlier. So this is the electric field after half wave plate. This was what we were supposed to find out. Let's just see what part A was. Determine the state of polarization of the light beam after the half wave plate. So we see that the polarization is linear. This is linear polarization, making angle 60 degrees with x-axis. So this is the polarization after the half wave plate. Now let us consider the effect of quarter wave plate. Now a quarter wave plate essentially converts a linearly polarized light into circularly polarized light. We can see that from here. So this electric field right here is elliptically polarized. This term over here is elliptically polarized, and if EF is equal to ES, then we have circularly polarized. So let us now see the effect of quarter wave plate in our given example. So for us, the incoming field for the quarter wave plate, and quarter wave plate is, by the way, along the fast axis of the quarter wave plate is along the x-axis. It is parallel to the transmission axis of P1. So if we draw this diagram again for the quarter wave plate, now if we take this diagram, or maybe I could draw a new diagram. Let's just draw a new one for quarter wave plate. So this is the x-axis, this is the y-axis. The incoming field for the quarter wave plate is the field after the half wave plate, and the fast axis is along x-axis. So this is fast axis for the quarter wave plate, and thus the slow axis will be along y-axis. So this is slow axis for the quarter wave plate, and this angle is 60 degrees. So we have the incoming field for the quarter wave plate is what we just found out after the half wave plate. Now the effect of quarter wave plate is to introduce a phase shift of pi by 2 between the component along the fast and the slow axis. So this component is along the fast axis and this component is along the slow axis, because our fast axis is along the x-axis. So field after the quarter wave plate is going to be as follows. This is the electric field. This I is essentially this, so a phase difference of pi by 2 is introduced. So this is our electric field after the quarter wave plate. So clearly we see that this is elliptically polarized, and the major axis is y-axis. Major axis is y-axis because this term is root 3 by 2, which is greater than this term 1 by 2. And the ratio of major to minor axis, in this case, ratio of major to minor axis is root 3 over 2 divided by 1 by 2, which is root 3. And then we need to check the handedness of the ellipse, whether it is right-handed or left-handed or clockwise or anti-clockwise. So to figure that out, we saw this in one of the previous videos when solving questions from quantum optics by Mark Fox. We will just briefly recap it over here. So when kz minus omega t, which is, let us say, phi, is equal to 0, we have the x component, the after HWP x component is equal to half, and the y component is 0 because of this pi by 2 term with the y component. So this would be e to the power I kz minus omega t plus I pi by 2. So when kz minus omega t is 0, we just have this pi by 2, and cos pi by 2 would be 0. We are looking at the real part of these complex numbers. So we are at this point to start with. This is phi equal to 0. Then kz minus omega t, so equal to phi is equal to, let's say, pi by 2. Then we have the x component as 0 and the y component will be, so this will be pi by 2 plus pi by 2 1, that is pi by 2 plus pi by 2 is pi, cos pi is minus 1, so this would be negative 1 times root 3 by 2. So this point would come over here. This is phi equal to pi over 2. So that means our ellipse is going in this direction. This is the handedness for the elliptical polarization that we have. So this is clockwise direction. So we see that the handedness is clockwise direction. Or equivalently, we see that this is left elliptically polarized light. So this is the state of polarization after the quarter wave plate. Now, the next part involves this P2 polarizer. So we want the orientation of the pass axis P2 to be such that after P2, this emergent beam should have maximum intensity and the polarizer works such that it allows only the component along its transmission axis to pass through. So thus we should have the transmission axis of the polarizer P2 lined up along the major axis of the elliptically polarized light coming after the quarter wave plate, so that maximum component of the light beam passes. That means we would then get maximum intensity possible. So part B, P2 transmission axis should be along major axis of the elliptically polarized light, which is basically obtained from the quarter wave plate. So that means the transmission axis should be along y-axis, because y-axis is the major axis. So this will give us maximum intensity. We can see that because this is elliptically polarized light and this y-axis is the major axis, so this is when the polar light beam is along y-axis, then that is the maximum component, and this maximum component needs to pass through the polaroid. Along the minor axis is a shorter component. This is minor axis, so the component of the electric field along the minor axis is going to be small. So this would lead to smaller amplitude, smaller component, so less amount of intensity being transmitted if we keep the transmission axis along the minor axis. So in order to get maximum intensity, we need to allow maximum component of the electric field to pass through the polaroid or the polarizer. So for maximum component, it should be along the major axis. So maximum component is along major axis, and that will lead to maximum intensity output. So this solves the question. The takeaways from this question were the use of half wave plate and quarter wave plate. So we saw what happens after half wave plate, we saw what happens after quarter wave plate. So half wave plate introduces phase shift of pi between the components along F and S directions, whereas quarter wave plate introduces phase shift of pi by 2 between the components along the fast and slow axis. So this solves the question.